Okay, can you hear me okay? I guess you can. Welcome to our weather discussion. This is the last one for a few weeks anyway that I'll be giving. Next week it'll be Chelsea, Snide, and Kari from 7:51, and then I've got the rest of the schedule. I just don't have it in front of me. I know Alex and Patrick are going to go, and then Angelica and Tim probably, I think. Yeah, I forget which weeks, but we know we've got the next 3 weeks scheduled out. So I want to turn the lights down. I can remember which one it is. Nope. That's the one. Okay, so here's our visible satellite movie for the last 6 or so hours, I think it is. Let's see. Yeah, it's more like 10 hours. Okay, so it's 10 hours over the continental United States. Pretty nice day across much of the country, clear over the eastern or western 2/3 of the country, and a really strong frontal band of cloudiness all the way from the far western Gulf of Mexico up into maritime and north of maritime Canada. And we'll see that's part of a structure that's really quite impressive and is well worth doing a little bit of diagnosis on. Today, we'll do that as we go through the forecast. The tropics in the Atlantic Basin are a little bit less active than we've seen over the last several weeks. There's a circulation feature well to the east of Bermuda. There's Bermuda. And so it's well to the east there. I don't know if that has a name or anything. I think it was one of those unnamed disturbances with a slight probability of development. It looks like it's a little bit better organized today than it was yesterday. Nothing down over the Caribbean and all the way to the North American mainland. And then some convective clusters on the south of the Yucatan, Nicaragua, Guatemala, that part of the isthmus. And one of these things, or something from that same region, is going to emerge as a threat to become Hurricane Epsilon in about 7 or 8 days, it looks like. Maybe slightly less than that. It's going to make a run. The forecast currently has it making a run at Miami, but it's going to be a little bit east of Miami in the current forecast prog on the 25th, 26th of October, or something like that. So still something to watch for in the Atlantic Basin for the rest of the hurricane season, that's for sure. And you might not be able to tell just looking at this satellite movie or the next one that I'll show you in a minute, what is the complexion of the large-scale circulation over North America and adjacent waters, but it's a broad upper trough and a fairly powerful upper trough, and I'll show you some evidence later on for what's really a really quite incredible cold air outbreak for mid-October. We'll be hovering around 2 sigma colder than normal at 850 for much of the next couple of weeks, well, next 10 days anyway, with only small interruptions of that. So last Friday, you remember I was crossing my fingers for not getting to 80 degrees in our howling southwest wind with warm advection, and somehow or another the airport reported 79 for the high that day. So we still have, as our last 80-degree day, the 2nd of September this year, which ties the all-time record for earliest last one. I don't think we're going to make a run at getting to 80 again this season. I think it's over. So I think we're probably going to tie that record. I meant to bring our current 850 cold pool, but I just didn't get around to it this morning. I have it calculated out to about the 15th of October yesterday, but I didn't bring it in and didn't fix up the diagram. So and I won't invade anybody else's talk next week. Maybe I'll just post it somewhere if you're interested so that you can take a look. But I think we're running way below normal hemispheric-wise, even though the fall season's been pretty nice and appropriately cold a couple of times otherwise. Here's the radar summary across the continental U.S., and a little bit of precipitation off the Florida coast is tied to this cloud band that's, oh no, that's separate, I'm sorry, that's a separate convective cluster. This is the cloud band associated with the front, and you can see the back edge of that goes all the way down to the far southern Texas Gulf Coast. Yesterday, some persistent moderate rains across the Piedmont, and today that's moved eastward ever so slightly into western New England and along the middle Atlantic states. So kind of a rainy day in those places, and temperatures dropping from, I think yesterday's high in the Boston area was well over 70, and then today, after the front finally goes through, it'll be in the 50s, so a lot chillier. That's a region of the country that this summer has experienced a severe drought, and that's not something that gets reported very often or occurs very often, but parts of southern New England and even northern New England, coastal northern New England, have had a severe drought this summer, and so this is a welcome rain for a lot of those locations. They really have needed it, and they're going to get a little bit today, as you can see. Across the western states, namely Montana, there's some precipitation in the central part of the state and the immediate lee of the high terrain. There's a little bit of precipitation working its way across northern Michigan and southern Illinois. That looks like it's tied to some sort of disturbance, and then some convective, perhaps, showers across the western part of our own state. Aside from that, not much going on anywhere else in the United States this morning. Here's the West Coast satellite image, and I want to point out a couple of features to you first. First, here's the state of Hawaii, just so you get an idea where we are in the mid-Pacific. And there seems to be a pretty decent cutoff upper circulation just to the northwest of Hawaii. And there's the center of it is almost certainly right there, because that's where the coldest cloud tops are, and that indicates most likely the deepest convective towers that are occurring because the air is coldest there and the water is relatively warm. So that's a pretty good indication of where the lowest geopotential height is, and it also coincides with the maximum in the counterclockwise or cyclonic circulation. And then to the north of Hawaii, all the way to the Gulf of Alaska, straight northerly flow, as you can see, southerly flow, sorry, heading poleward, and that's a big ridge across the west coast. So that's one broad scale ridge trough feature, this being the ridge. It's a broad feature. Watch some of the cloud elements here in the northwesterly flow across Washington State into the central plains of the United States. Yesterday was even more vivid. They were really racing southwest eastward. It's incredibly fast, and so one had an idea just looking at this radar summary that, satellite, that you were likely to have a really intense jet, and sure enough, that's the case. Did you have something, Greg?
If you look on the west coast visible, there's a lot of smoke again on
Oh, is that right?
there. Yeah.
Let's take a look at that.
Look at the enhanced color. Go up. Yeah, west coast visible.
Oh yeah, sure enough.
Just look at the last frame here, because it's
Yeah, so right in there, there's smoke in the valley, and there's little wisps of it. Seems like not clouds, but smoke coming off the northern part of the coastline. See that line there?
Yeah.
Then this one south to San Francisco. And as I was mentioning to 452 yesterday, I guess I will stop this on the last image. We are right now at the peak of the Santa Ana season, mid-October. It's not mid-September, which is what we just had. And so I don't know if these fires will really catch on. One of the things that's working against them is the anticyclonic center of circulation at the surface is offshore. And when it's onshore, that's bad news. That makes the flow offshore, and that dries things out and probably increases the risk of fires. So there's a little bit of a synoptic disincentive to really generate the big Santa Ana fires when they're supposed to occur mid-October this year. But there may not be very much left to burn in California anyway, so I mean, that's a whole other issue. But I hadn't noticed this, so I'm glad you brought it up. I was going to go to the upper level charts next, and here's the 500 millibar map from this morning, and we'll do a little bit of work with Vis5D in a minute to trace the history, or at least a recent history, of this extraordinary baroclinic zone that at 500 millibars is draped across southwestern Quebec, then through central Ohio, River Valley on Connecticut, the Indiana-Kentucky border, and then back through central Kansas. And it's a fairly continuously intense baroclinic zone, all the way really from Alaska up to north of Newfoundland. It's most intense right about in this location on the eastern Great Lakes region. And notice some of the winds along here, 90 knots, 110, 115. These are at 500 millibars. So these are very strong winds at 500 millibars, indicative of a really intense thermal wind, and that's consistent with there being a strong horizontal temperature contrast. And embedded within this is a broad upper trough. Remember last Friday we were talking about how this thing got established. It looked like the leading disturbance associated with a really powerful zonally oriented jet off the Pacific coast kind of pumped a huge plume of warm tropical air poleward, and that set the whole thing up, cut off this upper level low. And now look at the size of it. It spans the whole continent. And we were just looking at its partner upstream, the Big Ridge, which has roughly the same giant wavelength, both in the zonal and meridional direction. So these are large-scale wave features. They tend not to move very fast the bigger they get. And so we have a fairly substantial prolonged period of weather of one kind or another. For us, chillier than normal. Minus 34 at 500 millibars in Green Bay this morning. It only gets on the coldest days ever, and one of them would have been late January 2019. I think we were minus 46 or 47 at Green Bay. So it doesn't really get into another category of cold very often than it already is. And this is a widespread, you can see it plateaus at that temperature. It's all minus 31 to minus 34 in this huge pocket of real estate. That's about as cold as you can get in mid-October. Craig?
I was looking at the El Nino, and we're in a very, very strong La Nina now.
Yeah, that's right.
Near
Yeah.
record La Nina. The last time it was this strong was in 2010.
Hmm.
And in 2010, if you remember, we had the combination of the Meggy cyclone event.
Yeah, October 26th.
It was in November, I think.
Meggy was, the storm was October 26th here in the
Was
U.S.
it? Okay,
Yeah.
October. So right around now then.
That's right, yeah.
And so I don't know. This is a lot different than 10 in the sense that we have this deep cold trough, and I don't think it was that cold in 10.
It wasn't, but I was thinking about that setup last week when we were seeing this, almost non-stop zonally oriented jet at 200 knots almost. I thought, but this is just like October of 2010, so there's a lot of similarities. This flow has gotten wavier faster, I think, than what we had then.
Yeah.
But it's kind of the reason why I'm interested in, or I'm suggesting that there might be a period where the weather is going to be dominated by these features is that they're large wavelength features. They're not going to move very fast. It takes a long time to evolve when they're long wave features. But embedded within the trough, short wave number 1. There's a little bit of a short wave number 2 here. It's not quite as obvious. There's definitely a short wave number 3 here and a short wave number 4 there. That they're all finding their way through the trough, and those are going to be weather-producing features for the central United States. Maybe not every time right over us, but not far away in almost every instance. And all in the environment of much colder than normal temperatures. So that's really interesting. What we're going to do with Viz5D is look a couple of days upstream of this and just see what's the structure of this, first of all, the structure of the big upper trough, and then the structure of the baroclinic zone that is ringing its base on the southern side.
Can I ask one other thing?
Yeah.
This looks a little bit like a Rex block on the west coast. Would you consider that a blocking pattern? I'm not so sure it really is, but we do have the high over the low.
Yeah. I'd like to see the classic Rex block. Rex was a scientist, I think the paper was from the 50s, mid-50s, I think. I think the anticyclone and cyclone perturbations were about the same magnitude, and that's what's a little bit missing here. This is a weak anticyclone. This is what's left of Norbert, I think, isn't it? And so it's a really weak cyclone. We can see it in the satellite movie. I don't know if I mentioned it, but you can see it. But the anticyclone is quite impressive. Almost 6,000 meter geopotential heights off the coast of Oregon, mid-October. That's like Phoenix in July. So that's a really unusually intense ridge. And it's been stationary, and that's why we've stayed cold. So I'm not sure that it technically meets the criteria that may have been outlined in there.
I think you're
for a
right,
Rex
too,
block,
because
but it is
usually in the Rex-
blocking the flow.
In the Rex block, the southern,
What happened there? Sorry. I guess it'll come back. Yeah.
in the Rex block situation, I think the southern low would normally be part of a southern wave train. And it's not really what that is it? Because it's, like you said, it comes from Norbert. So it's actually a tropical origin.
Yeah, and it's kind of snuck its way in here underneath a really broad ridge. And this thing, I think if we went back and looked at a bunch of maps, which I don't think we'll do for time reasons, you'd see that thing has been stationary for really much of the week. We saw that there last week in one form or another. And that helped to establish this. What's really interesting to me is once the downstream trough gets broadly established, do they really start to work in sync to stay established as a pair? I don't know. I don't know enough about that large scale stuff. Angel thinks about things like this, but maybe not at this latitude. Okay, so that's a setup for what we'll look at a little more of this baroclinic zone. But remember, the precipitation on the east coast that stretched all the way from Gulf of Maine to mid-Atlantic, was most intense in the mid-Atlantic, is some distance to the east of the 500 millibar baroclinic zone. And I'll contend by what I show you in Viz5D, this is a continuous deep cold frontal structure. And so the precipitation's on way over here, but that's because the cold frontal slope is back to the north and west. And we'll see that when we look at other elevations here. So let's see, what does it look like at 700 millibars, for instance, in the same region. So here the baroclinic zone's a little bit further, closer to the coast. The most intense part of it is a little closer to the coast. Precipitation again was right here. And you can still see many of the same features at 700 that you could at 5. Short wave number 1, maybe you can see a new disturbance that wasn't so obvious at 500 millibars there. Another wave in here, third, fourth one, and even that one up on the border of the Yukon and Canada. And strong horizontal temperature contrast as far down in the atmosphere as 700 millibars. It's +3 at Quileute, Washington. It's -14 north of Calgary. So that at 700, that's a pretty good temperature contrast. And the same broad feature. Here's the big anticyclone sitting off the coast. The remnants of Norbert, making it look a little like a Rex block, but it might not be the classic Rex block. And the dominant continental scale feature of this deep upper low at 700 millibars. And one more level in the lower troposphere would be 850. That'd be one to look at. And at 850, the baroclinic zone is right along the coast. Not surprisingly, just about perfectly coincident with the precipitation band. Now look at some of these temperatures at 850. It's -5 with a westerly wind at 850 at Albany, +11 at Provincetown with a southwesterly at 25. That's about a 90-degree wind shift and a 6-degree temperature contrast. Halifax, this is broadly warm air. It's 11 there. It's 11 at Caribou, and it's colder as not Caribou, near New Brunswick, and then it's 6 at Caribou. It gets colder as you move to the east. Here down into the west, 16 in the vicinity of Newport, North Carolina, 7 degrees in interior Virginia. So there's a 9-degree temperature contrast across there. So this zone, if you had a pencil and you were drawing this yourself, you'd do a better job in the computer. It'd be a really sharp baroclinic zone at 850, all the way down the coast. And the precipitation is just along the leading edge, the warm edge of that. And yet you still see at 850 the same features we saw aloft. Substantial ridge off the west coast, and this is a little bit more of a double-barreled low, but nonetheless a broad cyclonic circulation centered over the western shore of Hudson Bay, but dominating the whole continent. So it's really a nice set of pictures here. So what I want to do now is do a little bit of analysis on 2 features of interest from what we've seen in all of this. One of them is the upper front, upper trough feature associated with this whole complex over the eastern U.S., or over the continental U.S. I got to get my control window back here. Get out of the way, please. There it is. Okay. So first let me make this window bigger, as big as I can, and then I'll zoom in a little bit. So what I'm showing you first of all, let's get you settled on where we are. This is 0Z from Thursday, so I'm using the 0Z GFS run from Thursday. I know that's a day and a half ago, but that's on purpose because I want to see the evolution of the structure that we can interrogate at about the present time. This is approximately 500 millibar level. It's 5.4 kilometers above sea level, and the light-colored lines here are isobars every 5 millibars. So that gives you an idea of what the 500 millibar flow looks like. And it's not surprisingly, it's quite strong across a ridge, a crest over the western United States, and then dips into a broad upper trough across much of the central part of North America. Then the red lines are theta lines at the same level. So one can see some pretty strong cold air advection just to our south and west, and then a little bit of cold advection along the cold side of this baroclinic zone, even further west than that. Cold advection in cyclonic shear tends to force the sink on the warm side and maybe rise or not rise at all, or not move at all in the vertical on the colder side. And so the tendency is to start to intensify the baroclinic zone by tilting when you're in the middle troposphere. So if I take the pressure off, just so you can see theta, and I wish the map didn't have all the counties on it at this time, but nonetheless. Let's step forward. These are every 3 hours. Maybe I'll take the map off, just so you can see the intensification of the baroclinic zone. I'll put the map back on in a minute, but this is 12Z Thursday, so here's a really sharp baroclinic zone, and it stretches all the way from Hudson Bay up to the ridge crest. I think you can see these are every 3 degrees Kelvin. So this is a synoptic scale feature, planetary scale feature really, and there's the map to show you where it's all going. And then step a couple more times, and you can see it continues to get more and more intense, especially at its base. So this is a pretty good time to take a cross section, but here's the pool of really cold air at 500 millibars that we just saw, you know, the minus 30 or colder air. And then it's surely tropical to the south. Let me remind myself where I put my cross section. That'll help us see where I should be doing this. Yeah, I think I'll go back a couple of times. I think that's the time I want to look at. So 12Z Thursday, just to get an idea what this thing looked like. Okay.
Why don't you just try reversing the video? You might be able to see all that better. Just go down one notch down, right where your arrow was. Go down.
What?
Go up a little bit. Just say reverse.
Oh.
No, that's worse.
Yeah, it doesn't help. I'm going to just take the map off most times. Just I'll put it up there every once in a while so you can see.
You can color it a lot lighter too, you know. You can just turn down the intensity. Just go put the right button.
Oh yeah, you can.
And yeah, and just pull down the intensity of the colors.
We can change that map so it doesn't have all the counties on it too. I'm sending you an email right now just so I don't forget.
Okay. Yeah, that's a good idea, Greg. That looks better, doesn't it?
Yeah.
Yeah, okay, you can see that now. Okay, so let's take a cross-section through this upper baroclinic zone right about at this time. And I put theta on there already, so I'm just going to flip it up so you can see what it looks like. And here's why I say this is, I'll go like this. Here's evidence for why I think this is a continuous baroclinic zone all the way down to the ground. Look at that bundle of dry isotopes. This is 306, that's 309, 303, 297, 300, 303. So 303 to 309 is part of the upper front, and it's also part of the surface front, all the way down to the ground. So this is a relatively rare structure. You don't see this all the time. This is a really deep front. And I decided to pick one of the theta values to show you the vertical structure of this, and there it is. So let me just roll around here a little bit. Somehow I got the color wrong. I thought I had done this by pressure, but it decided to change on me. But I think you can see, take all this off. Look at the deep, it's like a steep column of cold air, or a deep dome of cold air that's just sitting over the continent. And so one of those isotopes, here's the cold pool that sits there at 500 millibars, and then there's this steep slope all the way down to the ground in the western U.S., and that's where the front is hitting the ground on this cross-section line. So I don't know, maybe this isn't so useful to see, so I'll put these back and get rid of that. Okay, so there's the baroclinic zone. And I want to put a couple of other things on this cross-section. One of them is the speed, the wind speed. So here's the wind speed every 10 meters per second starting at 30. And not surprisingly, we have the strongest horizontal temperature gradient, you have the strongest vertical shear. And that's true not only in the troposphere, but also in the lower stratosphere. Here's a strong temperature gradient. And it's the opposite way. It's warmer on this side and colder on this side, so that the shear is coming out into the page and this way. Well, let's see. The shear is reversed, and so the wind speed decreases as you go up in through that baroclinic zone. But an isotope like 360 or something has a really steep slope up in here. So there's a lower stratospheric front and there's an upper tropospheric front, and they're branched off at the jet core. And then there's this really weird region of poor stratification, which we've mentioned other times before, where the PV is really low. You have anticyclonic shear and you have low stratification, the lowest PV that you're going to have. Where this came from in this case is not so obvious to me. Yeah.
I can point out that's clearly a polar jet there, because the isotope that goes horizontal through the jet there looks like it's about, what, 332?
333, yeah. This one right
333. Yeah, so that's clearly, because a subtropical jet, the horizontal isotope's about 355.
Yeah, well, yeah, somewhere in the high 340s or low 350s, yeah, that's right. So this is a totally different beast, and it has a really strong lower stratospheric front associated with it as well. And if you, let's see, the PV structure is rather interesting too. Let's get there. I think it's easier to see if I take the winds off. So there's what the PV looks like. And this is the 1, contour 2, and so on. So it's fairly steep wall of PV, but it doesn't go down. This is 5.4 kilometers, about the 500 millibar level. So the 1.0 PV surface doesn't even get to 500 millibars in this case, but it's a pretty intense wall of strong PV gradient. And that PV gradient is coincident with the jet core. That has to be the case. And anyone can see these relationships.
But you know, there's
all the time.
another 1 PV unit contour down there toward, so I bet if you just went down to half a PV unit, you'd get a continuous PV all the way down.
Could be, yeah, and this one is way off in the cold air.
Well, look at the one in the Bear Clinic.
Oh, and
right
there's the
there.
one in the Bear Clinic zone, yeah.
I'm
yeah,
thinking.
Oh,
that-
0.5 would do this.
Yeah, the 0.5
Yeah.
would do that, in which case you might be able to suggest that there's ozone coming down with it.
Let's see, because I'll show you another variable too that would suggest the same thing. Let me just change that. I'll just do 0.5 all the way. Let's see if BizBuyD knows what to do there. Doesn't really know what to do, but there's the 0.5 is added in. So it's almost continuous, but not
I'm
quite.
sure there's at some level it's continuous.
You could find a value that
And
does it,
it's
yeah.
just a matter of resolution and what do you call it, taking maps and interpolating one map to the next map, you lose it. But
Yeah.
I'm pretty sure that's a continuous surge all the way down.
Yeah, and there's reason to believe that, and I'll show you why. So you anticipated this. Here's the vertical motion. This is just the subsidence. Did I have that in the right place? Thought I did, yeah. Okay. I didn't write down the time that I looked at, I guess that was stupid. Let me see what I'm contouring here. That's subsidence. Okay. I had a more dramatic example, but this one suffices. If I take the PV off and put the speed back on, yeah, this suffices. Right underneath the jet core, there's strong subsidence, and that's tilting the isotrope. But it's also draining the lower stratosphere of all sorts of different things, including PV, ozone, who knows what else. And so that subsidence is definitely working in favor of exactly what you said, Greg. I'm going to click ahead and back a
But you know,
time.
there's actual, Mel Shapiro's done a lot of these studies. You can detect ozone at the surface when this happens,
Yeah.
coming out of the stratosphere.
This is a slightly earlier time, and this is the one that I saw when I was at home getting ready for this. This is still subsidence, and this is along the same cross-section, but at a slightly 3 hours earlier time. This is the subsidence that I saw, and look at how sharp that is. That goes all the way down to the ground. And so that's doing what you said. And then you'll see, in addition, here's the ascent, the same contour interval. So look at this isotrope right in here, for instance. This thing's being forced to sink on this side and rise on this side. So that's tilting the isotropes even more in the vertical, in the whole lower troposphere. And then in the upper stratosphere, or the lower stratosphere, it's interesting. This baroclinicity, these isotropes are being tilted the wrong way. But when you get past this subsidence over here, it's starting to redo the tilting of the isotropes in the right way. So the baroclinicity right in the jet core is weakened. Baroclinicity out ahead of it is strengthened by the tilting in the lower stratosphere. So this is really, really interesting. And as Greg points out, ozone is an air quality issue regulated by the EPA. So if you have, pollution in your boundary layer and it can't mix out and you create ozone because of smog, that's one thing. You should be penalized for not figuring out how to fix that. But should you, it's a reasonable question, should you be penalized for being here at the base of a column of air that's draining the lower stratosphere of ozone and therefore enriching your boundary layer with poisonous ozone? Probably not. So having, a way to differentiate between synoptically forced ozone events and those that are forced by pollution and bad regulation of your automobiles or whatever it might be, that's an important public policy question. Brad Pierce is working on that all the time. He's the head of an informal consortium that thinks about exactly that issue and how are we going to create fair ozone standards. That's a very reasonable question, but it's completely related to the structure of these kinds of features, and they become ubiquitous at this time of year. You see them all the time.
And another thing
So
is,
it's a big deal.
this is one of the few mechanisms to clean out the stratosphere, because you put stuff up there a lot of times. It stays
Yeah.
up there for years.
Yeah.
This is one of the mechanisms that ventilates the stratosphere.
And it happens all the time in the cold season, all the time. So that's a really good point. And some of the attendant ascent in the convective plumes that can develop pushes water vapor into the stratosphere, and that's a foreign quantity for the stratosphere. So there's all kinds of exchange of chemical constituents going on. And as Greg points out, this is like cleaning the attic. And it has to be done every once in a while. And luckily nature provides us that with regularity. Okay,
Hey, John.
so one last thing I
John.
wanted to show you from the Viz 5D.
John?
Yeah,
Question from Ross Lazier online. Is the upper level subsidence upstream of the trough axis also playing a role in reducing the stability in the upper troposphere in the cross section?
I don't know yet. That would be a good question to ask. This, it's a very good question. This reduced stability pocket is not exactly coincident with the subsidence. It's coincident with part of the updraft, downdraft couplet, but I don't really know what the mechanism for having produced this poor stratification air is. I have a guess, and one would solve that by just initializing a whole bunch of trajectories in this pocket, seeing where the air came from, and I'm going to guess that air is of tropical origin. I think it's probably gently rose from the boundary layer in the tropics, found its way on the anticyclonic shear side of the jet for reasons that might have to do with transport of chemical species and precipitation in prior times and so on. That's probably my best first guess. Because it's hard to make low PV air in the stratosphere. You can't really do it because the stratification is so strong. It's easy to make low PV air in the boundary layer. The trick is how do you get it to get up to the middle troposphere?
Well, if you get subsidence, it will spread the isotopes, right? I mean, and that's a destabilization process.
Well,
if it, it has to start somewhere. And if it doesn't start in the stratosphere, if it's in the troposphere, you get a divergence.
yeah, at the top of the subsidence column. Yeah, that's right.
Well, where the subsidence is accelerating downward, that's going to spread the isotopes.
Yeah.
And that's a destabilization mechanism, but it doesn't create a lot of unstable air for lifting unless you slip underneath it some moisture, so convection can poke up into that layer. But it does steepen the lapse rates at mid-level from the subsidence.
So that depends on the vertical gradient of W or omega. And in some of this
that's right,
region, there isn't much vertical gradient. It's just a sloping column of subsidence. But where there is a vertical gradient, you'll have a change in the stability. That's true. Yeah. When it's d omega dp is positive, you're going to weaken the stratification, and opposite when it's negative. Yeah. So that's a good question. One other thing I wanted to show related to this, and as you know, you could go on all day with this stuff. It's just so interesting and so full of information. But I want to just show one last thing, and that is the PV structure. I hope this maintained the colors. Yeah, it did. So that's the PV structure of the 2 PVU isosurface. Let me put this on top of it so you can see where the baroclinic zone is. At 500 millibars. Now this would be lower than this surface, but that's why I had to lift it up artificially. But you can see where the gradient at theta is strong, that's where you have, I'll take it off in a minute, that's where you have the greatest difference in height of the tropopause. And so these are all consistent with it, with each other. So let me show you this structure of the tropopause. So there's our trench. I think you can see kind of nicely. I'll go to the north view and then tilt down this way. So that's our trench in the tropopause from a different view. So this red is where the tropopause level is really low, and the blue is where it's really high, and that's a steep drop off. And there's always a front edge to such a trench, and that front edge has a relationship to development in the lower troposphere, and that's what I want to show you. And then we'll quit. And that is, I'll put the mean sea level pressure on top of this. And these are only isobars with values lower than 1,012 millibars. So this is 1,012. And right at the front edge of this pendant, or this deepest part of the tropopause trench, pendant of high PV, there's our little bit of a cyclone. Here's another one where there's a local maximum or minimum in the height of the tropopause, which would be a maximum in the PV. There's another cyclone. This one's sort of off on its own, but it's over the Intermountain West, so it might be orographically induced. Let's go ahead a few times. So there goes cyclone number 1 up into Canada, and it stays tied. Cyclones 1 and 2 stay tied to the regions of locally high PV, low pressure on the, or high pressure on the tropopause. And if we keep on going, I think there's going to be another storm. There's one up there in northwest Canada that follows the same rule. Here's the low tropopause or high PV, and just downstream of it is where you get your cyclone developing. And that becomes a pretty intense disturbance. Look at this. This is, I think, Saturday, Sunday, which I'll talk about a little bit in the forecast. Again, a very deep trench. This one not quite as lengthy, but the front edge of that deep trench, where the PV gradient is largest, is where the cyclone develops. And watch how this thing goes to town. So that's a pretty nice development. And that's by this time over Hudson Bay in central Canada. So there's some really nice relationships here that are, characteristic of the way the mid-latitudes works. And you can see them with this visualization stuff with ease. And we don't have enough time to do more diagnostics on them, okay? But are there any questions or comments about this stuff before we move on? Greg?
Well, I think this tropical, whatever it is to the south of the jet is interesting because there's not a lot of very low potential vorticity. I mean, there's low potential vorticity, but not real low, extremely low potential vorticity. So this doesn't look like a tropical plume, at least a new tropical plume. It may be a very old one.
Where are we?
Oh, the blue streak underneath the red.
Right here?
No, up there, coming around that way. Yeah, when you looked at that
Yeah.
and tilted it back, that's actually a ridge, and the yellow there on the south side of it is a trough.
Yeah,
so
that's right.
This is a ridge plume coming around there. It's not high enough or low enough potential vorticity that it looks like it has any recent tropical origins. So the question is this cold air up there lifting this, or is it coming from maybe an old subtropical jet somewhere way upstream? I'm not sure. But it's definitely an isolated ridge that's moving
Yeah.
along the southern side of that.
Yeah. There were times earlier in the week where it looked like the jet off the west coast, even though rounding the base of the ridge, or the crest of the ridge, looked like a really intense superposed jet. So I'm not sure there isn't some subtropical history to that region of low
It
PV.
must have been way
south
back
of that.
by Asia or something.
Yeah, I didn't trace it back, but that's quite possible because it was a week. This week was really a week of an extended jet across the Pacific too, deflected poleward into the ridge. But so there might well be such a connection.
I just try to think of the morphology, because whatever that ridge is, it's definitely connected to this trough.
Yeah, they've
And
been
so
made
if it's
to be
coming in
connected.
from Asia, then Asia is causing this cold air outbreak over us.
If that's true.
If that's
Yeah.
true.
Yeah.
But that's that's the way I look at it.
Yeah.
I think those connections exist.
Yeah, and they might very well exist in this case. Yeah.
When you're looking at potential vorticity like this, it's very conservative. It's almost completely adiabatic at these
Yeah.
levels.
Yep. Yeah, so I mean, the production of these kind of thousands of kilometer long trenches in the tropopause is a real. I mean, I think we think we understand it, and we don't really understand it. I'll be honest with you. I think the processes that dig a trench locally don't dig a trench across the Pacific Ocean. It's a little different. So there's something really interesting there.
It's one of the most fascinating things in the science right now.
I agree. I couldn't agree more. I can't stop thinking about them. As you know, I've been thinking about these things for 20 years because I'm interested in them. Okay, what I wanted to do next was another special focus, and that is on our cold air outbreak. So these are really nice maps that are made by Alicia Bentley. Unfortunately, they're immune to zooming in. I can't get them bigger than this, so I'm sorry about that. This is the 850 millibar temperature anomaly that is shaded, and these are in standard deviation units. So if there's nothing unusual, there's no shading. If you get to 0.5 standard deviation warmer than normal, you're yellow, and so on. And 0.5 or more standard deviation colder than normal, you go blue to purple. So this is from, what time is it at? This is valid at noontime yesterday, 2 days ago, noontime Wednesday, when we had a really nice warm day. Remember that, how warm it was on Wednesday? It's the last warm day of the year. Even though it was cloudy, we got to mid to high 60s. It was unbelievable. And we were just a little bit in southern Wisconsin warmer than normal. And the actual 850 isotherms are also on here in red, and the geopotential heights are black. So this is maybe the last time for quite some time that we'll see a positive anomalous standard deviation of 850 temperature, as it turns out. There's this pocket of really colder than normal air, and these are all, of course, normal for that spot in Canada, Great Slave Lake. So that is 1.5 to 2 standard deviations below normal. Then the next little blip is 2 to 2.5 standard deviations below normal. That's a lot of colder than normal for that region. And so when the Wednesday disturbance went by to our north, gave us that little sprinkle around 5:30, that was really the beginning of the end of summer, I think, because you'll see this cold air on the western side of the big disturbance to the north just keeps coming southward, watch. So this was, these are every 6 hours. So this was midnight on Wednesday into Thursday, and we first get into the lightest blue, 0.5 to -1 standard deviation colder than normal at 850, and there's nothing stopping this really cold air from coming in. And if you can see Wisconsin there, a full day later, we spent a whole day in really cold air. This is actually 12Z this morning, so we're still in the 1 to 1.5 standard deviation below normal, with yet colder air poised to the north and west in northwesterly flow. So how does it avoid us is a good question. And notice that all the way down to the Rio Grande Valley, across the border into Mexico, colder than normal at 850. Almost the entire country, except the immediate east coast, which is right on that frontal boundary that we were talking about earlier, is colder than normal at 850. And that presumably means colder than normal at the ground. And here's where the precipitation was, right along the leading edge of that front. So this is a bona fide cold air outbreak. The kind that if it comes in January, you can forget about summer and fall orange juice and all sorts of other things down in Florida. No cherry tomatoes for the winter or any of that. It's all gone. Strawberries, the whole thing. So this is a really serious cold outbreak. It's just lucky that it's mid-October, that the air isn't that cold that it does damage to all those things. But watch what happens as we go forward. So this board is now into forecast time. This is now 6 hours into the future. Just see how long we stay blue. We get a little bit of a reprieve to be almost zero perturbation, which would be just about normal tomorrow night, before the next really strong punch of cold air comes in. So tomorrow might be a decent day. It'll be maybe a little bit on the chilly side in the morning, probably recover in the afternoon, but it won't really deviate much from normal at 850. But then by Sunday, we get the next push over us of chilly air, and that is going to stay how long? I think at least through the 20th, which is, I don't even know what day that is. Is that next Wednesday or something, or next Tuesday? So that's chilly all the way through the early part of next week. And all of Canada just about is colder than normal. And that means, I don't know, it means a whole bunch of things to me. It means that the Western Hemisphere is likely, that's the region where cold air is produced in the Western Hemisphere, maybe a little further to the north and west. If it starts out cold and maybe gets some snow on the ground, it's going to get colder faster and earlier. And so these forecasts about La Nina giving us a warm winter that I just read about today, I just don't know. I mean, La Nina signal for us for temperature is never very clear, number one. And number two, I don't know, if you start out like this in October and early November, I don't know how you recover from that, at least through December. It takes a while for that to maybe get ameliorated. So if we keep on going, I think only by the time we get to about this time, we're still in the blue. We're still a little bit below normal by midday in the middle of the week. And then I think we just avoided being above or below normal for a little bit of time near the late part of next week. But then we get another substantial cold snap that's going to come in by, what is this, about a week from tomorrow. We're into the -2 standard deviation. So when this cyclone goes by, that's it. We have this whole continent north of us that's colder than normal, funneling air over us that is certainly going to be colder than normal here.
Looks like the next storm, Epsilon and Zeta, are on that map.
Oh yeah, there's Epsilon, and that's, this might be Zeta, is that right?
No, the newest one, after
that's it.
Epsilon comes Zeta.
So it is going to be Zeta. Zeta is going to be the one
But I
that's
think that one up
wild.
there is actually the Epsilon, because
Okay,
they're pretty late.
okay.
What day is this, October?
24th, which is a week from tomorrow. So this
No,
is 0Z.
you might be
October.
right, 24th might be, that might be epsilon up there and zeta, I don't know.
Yeah, I don't know either. We're gonna look at this a little bit more in the forecast, because this is the next interesting question. I just wanted to give everybody a heads up that we're not gonna get out of this chill in any substantial way for the next 10-ish days. That's the way it's gonna be. And the October 23rd is the last time, I don't know what year it was, 2006 maybe, is the latest 80-degree high for Madison. That is not going to happen this October 23rd. There's no chance that that's going to happen. So if it comes later, which it could, we would break that record, but it doesn't look likely.
When is our first sub-10 high?
Oh, I don't know. I don't have it at my disposal to look it up quickly, but I don't know. That's a good question. That's a good question. I don't know. Okay, so the next thing I want to do is just do a little bit about the forecast for the weekend mostly, and then we'll go forward to look at this very interesting stuff that's on the doorstep for early next week, 25th, 26th of October looks interesting. Just say a word or two about that. So here's the 300 millibar wind speed forecast, valid tomorrow morning at 7 a.m. So this is a 24-hour forecast. And when you have this broad zonal flow across much of the country, that often means that it's warmer here than normal. Now, that's because you tend to get a nice subsidence in the lee of the Rockies. The problem is, at least at northern latitudes, the flow here that might help to do that is more or less parallel to the Rockies. So it doesn't really produce much warming at our latitude immediately to our west, it doesn't look like. But there's some interesting, this strong upper level low that's sitting over mid-Canada is really dominating the flow over North America. 500 millibar vorticity at this resolution is really hard to really see coherent structures, except when they're really, really obvious. And the one on the East Coast this is that upper front, and down sheer of it, there's PVA by the thermal wind and cyclonic development going on tomorrow morning over northern New England and maritime Canada. There's the remains of Norbert. Looks a lot more impressive at 500 millibars than it does at sea level. Here's the big ridge, 5926 off the west coast, and 5205 for the cutoff low just south of Churchill, Manitoba. Little bit of upper vortex structure. This might be a weak wave number 1 that comes in this broad upper trough. And so down sheer, that one has to be concerned that there'll be some forcing for ascent over eastern Minnesota, western Wisconsin. Here's what it looks like at 8:50, and there's the cyclone exactly in that spot, developing over central Minnesota. A strong southwesterly flow across the region and dragging warmer air across our region. We're starting out around 0 at 8:50 to begin the day. So tomorrow will be a little bit of a warm-up compared to today, but there might be a threat of a little bit of a shower as well, simply because we have differential warm advection and over this region of the state some PVA by the thermal wind. So some forcing for ascent over the western part of the state as the day dawns tomorrow. And I think that's shown at sea level, the same forecast. Here's the cyclone, about 1,000 and, what is that? Can't read it. This is 1,008, so 1,003 millibars maybe in spa southwest Minnesota. On the northern periphery in the baroclinic zone, there's forecasted precipitation, and it spills over into the western part of our state. Doesn't appear to affect Madison by 12Z. Okay. But you can see what's coming. Right behind it, there's strong cold air poised to make an appearance. So I'm jumping ahead 24 hours at a time so we can make it, or 12 hours at a time so we can see what happens on Sunday. Here's the strong upper level low jet streak on its southern periphery, and not much to say about that. Big ridge over maritime Canada. So the whole flow is kind of blocked up a little bit. 500 millibars, that upper vortex substance or vorticity is kind of making its way across the northern part of the state. So that's probably where the cyclone that we saw over central Minnesota will be moving in this direction. That'll drag the front across us probably by Sunday morning, which is, this is Saturday night. And so we'll see what that looks like. Here's a big storm in Canada. So at 0Z tomorrow night, there's the cyclone over the upper peninsula, exactly where it should be relative to all the forcing. And here's a strong baroclinic zone. Look at how sharp that temperature contrast is. This green right here is something like plus, it's not labeled, plus 14, and I think that the light blue here is 0. So there's a lot of temperature contrast in there. And here we are just about seeing the 850 front just to our west. Maybe the surface front is just about on us by 7 p.m. tomorrow night, 6 p.m. tomorrow night. And so it'll get windy, probably a little bit of a gustiness and some strong temperature contrast, some strong temperature changes within the hours surrounding this time over Madison. And very cold behind at 850. And there's the cyclone center at the same time. A little bit of the puff of precipitation is on the northeast side of it. Nothing for us, but the thickness contrast indicates the front is right through Madison at that time, just coming through. Strong cold advection back behind. So it's going to get much colder overnight tomorrow night. And then not much of a change at 300 millibars for 12Z on Sunday. 500 millibars, you can see the thin strip of vorticity that's probably tied to the strong baroclinic zone at upper levels, much like what we saw today in the diagnosis. At 850, where is it? Oh, right here. At 850 at this time, it's clearly frontal passage has occurred. Because here's the warm edge of it down over southwest Kansas, and we're well to the north. We're in the -2 to -4 range at 850, 12Z on Sunday. If there's any precipitation floating around, showers or anything that might not be forecasted by the forecast model, there isn't anything. There's a little bit down here in Iowa and Nebraska, a little bit in the lee of the lakes in Michigan, and there's a gap right here. If this gap is filled in by a shower or two, that'll be a snow shower. So Sunday morning will be cold, and if there's a chance of some convective shower, it'll be a snow shower, in my opinion. And then, not much change for, this is now 12Z Monday, a full day further ahead. And you can see that just continues to be wave upon wave at upper levels in the northwesterly flow. Here's one over the west coast of Alaska that's going to slide perhaps down into this northwesterly flow and further deepen the Hudson Bay low, which is established very nicely by mid-October this year. So
there's a pretty nice one there in North Dakota.
yeah, that's a sharp upper wave. That's right. It's a sharp upper wave. Right in here is Greg's talking about. So it's local maximum and cyclonic curvature, and that's going to swing around the base of the trough. So there's more than one in these broad long wave troughs. And the one in North Dakota has its own little vorticity signature, which is right here, a local maximum in the vorticity. The one further upstream has one also, and then the one in Alaska has an even more impressive upper vortex structure. So it really does look like 1, 2, 3 waves in a row with even spacing, which means temporally they'll come at an even interval. And here's the 850 map. We're still cold, just about as cold as we were. I think the temperature advection has stopped in the northern part of the state. It's just occupying the southern portion of the state. And so we stay cold for Monday morning, but we don't get any colder. It's not actively getting colder by advection at this time. And then finally, the forecast at sea level, broad anticyclone, fairly weak one across us, probably cloud-free Sunday night into Monday, 540 thickness line, -3 at 850. This is the widespread frost. If we haven't already had that, we might have had it last night, but we will one of the days this weekend. There's almost no doubt about it. And the little trough across North Dakota spawns some weak, almost certainly snow showers across much of the western half of South Dakota in the forecast. So this is quite remarkable. 19th of October, 2 years ago, Game 7 of the NLCS against the Brewers against the corporate LA Dodgers. It snowed on the 20th of October here. And remember that there was a football game here in town too. It was snowing enough to cover grass and leaf piles with snow. So this is looking like the same kind of large scale setup, but maybe not quite enough chance for precipitation while it's cold, is what it looks like.
Well, you don't always see it in this because a lot of this is instability when it comes through.
Yeah, it was that day
Ground's
for
still
sure.
warm, and so you can get some of these convective showers in the late afternoon or in the early afternoon.
That's what I'm hoping. So it can certainly happen. So here's what I want us to end with, and this is this is immune to zoom in as well. So this is now, I'm going to back up a couple of times. This is from the GFS this is about the time that we were just looking at on the last of the 850 charts, I think. So one of the tropical disturbances, it's either zeta or epsilon, and this one's either zeta or epsilon. And it's in the, between Cuba and the Yucatan Peninsula, this one out near Bermuda, which is right there. So some pretty unsettled weather. Notice how cold it is over us. This is valid next Friday. And so very strong cold advection, 529 or 30 thickness sitting over Madison with continued cold advection, precipitation to the south and east, but very cold, very chilly day next Friday for us.
I should mention, if we do get a zeta, that's gonna tie the previous record for number of storms in one season.
Oh, is that right?
In 2005, we had a zeta, but it was in January. So it was
Okay.
actually in 2006.
Yeah, wow. So we could,
So we're, and this is in October yet.
yeah, it's unreal. Because we had a Hurricane Karen in November for 1 year,
Yeah.
right?
Yeah.
It's unbelievable. So we can get hurricanes, full-fledged hurricanes in November, and we're not even close there yet. So we might get well into the Greek alphabet. Everybody will be boning up on what those letters mean. So those are the two tropical disturbances, and there's an extratropical disturbance on the eastern edge of what looks like a strong jet flow, and you can say that because the thickness gradient's large. Watch what happens. No diagnosis, just watching what happens. So here comes, these are every 6 hours. Here comes Zeta, if it is Zeta, brushing past Miami as a very intense disturbance. This is a 962 millibar disturbance right through the Straits of Florida. This is 971 up on the western coast of the Labrador Sea. So this is a very intense and broad scale circulation that's really dominating the North Atlantic. An anticyclone dominating the eastern third of the United States, and another one coming out of Canada to supplant that domination. So it's going to stay anticyclonic and chilly in the northern states. But look at what happens with this disturbance. Woo, boy. It gets just more and more interesting. This thing gets more intense. 958, it's going to maybe have brushed. It's certainly going to go right over the Bahamas, maybe a little bit on the far southeast coast of Florida. Then it's mostly out to sea. Warmest waters in the hemisphere are right here. The so-called Charleston Bump has the warmest water around. Then it's going to go just offshore of the Carolinas. Here's almost no real obvious circulation center except a widespread region of precipitation because it's a strong frontal boundary moving into probably tropical warm, moist air. But these two things get their act together, in this forecast at least. Look at this.
Perfect storm.
Yeah, it's unbelievable. So this thing is now 958, sitting just south of Halifax, Nova Scotia. Incredibly intense circulation. You don't want to be in a vessel out here. That's dangerous, deadly. And then on the back side, a new disturbance gets itself going on the strong variclinic zone that's left behind as the anticyclones moved in. Here it is over like Beaufort, South Carolina. What a week it's going to be on the East Coast. So New England gets hammered on, this is valid Tuesday the 27th, 0Z. And then the next storm wraps up as Epsilon, Zeta, whatever it is, starts to head toward the Canary Islands. 973, an incredible disturbance right up in the Gulf of Maine. Extraordinary winds, strong cold advection. This will be mostly snow in southern New England if this verifies, including the Boston area. And then watch Epsilon, right over the Canaries. 951, that's 961. At one time, it's stronger as an extratropical storm than it was down here. Incredible, same exact location. These people's huts are just being, the sticks from their huts are being picked up by the time the next one comes along. I mean, of course, I'm exaggerating. They have fine dwellings, but an incredible disturbance. Look at this occluded thermal ridge in there. And there's the old hurricane. And where's it going to end up? It's rotating around the giant subtropical high, but it's maintaining some structure. Look at that thing. All the way almost to the Cape Verde Islands. Just about where one could argue it may have started. But it didn't, because this one started in the Caribbean. But this is a place where a lot of these African easterly waves come right across the Atlantic. So this one started down here, went up like that, ends up right there. And there's a massive storm in the North Atlantic. So strong positive NAO, screaming jet across the Atlantic, all because of developments that have occurred in serial fashion along the East Coast. So a really dramatic event coming up early next week, 25th, 26th, 27th of October. So we have to keep our eye on that. It's a lot of time between now and then, so the forecast can change. I was going to show you some alternative forecasts from a few days ago for the same time period, and they're totally different. So there's plenty of variability that's yet to be seen. But there are some elements that keep propping up at various times that probably makes you think that they're likely to occur in one way, shape, or form. So any questions or comments? Okay, if there are none, then we'll reconvene next Friday. We'll have Chelsea and Kari running the discussion, and maybe you'll have some both extratropical and tropical things to talk about. Looks like that's going to be the case. Pete, thank you for helping set up, and Greg for the conversation as usual. And to see you all next week. Have a good cold weekend.